Okay, here I have a function defined piecewise, and I've called it f. It is a function, it passes the vertical line test, and it's a collection of points. Remember, a function is simply a collection of ordered points that has one y value for every x value, and we can use the vertical line test for a graph to see if it's a function, and every vertical line that I draw only intersects the graph one time. It doesn't matter where I draw it. Even if I draw it over the y-axis, you can see it looks like it has 2 points, but this point here is filled in and this one is not. So it's showing that only this point is part of the graph, okay? So it is a function, and we say it's defined piecewise because it's not linear, but it has 2 pieces that are linear functions, and it's glued together kind of, if you will. So we can write this function symbolically, and I'll show you how we do that. So here we have f of x, and since we have 2 separate functions that we are piecing together, we're going to go ahead and write those, the representation of those functions here in slope-intercept form. So on the left, you can see the slope. If we travel from this point up to this point, we rise 2 units and we run 1 unit, and it's up 2 over 1. So the slope is 2 over 1, or 2 times x, and then you can see the intercept, the y-intercept value is 3, so it's plus 3. And then on the left, we have another linear function. This time we're going to have negative slope, because when we travel from here to here, you go down 1 unit and over 1 unit. So the down in the y direction would be -1 over 1, which gives me -1, so negative x. And the would-be intercept, it's not actually intercepting the y-axis here, but imagine if that point were filled in, the would-be y-intercept would be +1. So we have 2 representations of linear functions, but we have to specify when the function is represented by 2x plus 3 and when the function is represented by -x plus 1. So we do that by looking at the x values. And for this linear function to the left, you can see it goes down forever if you're going this direction, but it's actually an increasing function, even though it's pointing down. Remember, we read from left to right, so it is increasing, but it's also coming from the negative infinity, right? So it goes forever in this way, negative infinity. So negative infinity all the way up to this point right here, which lines up with this point. Now this point is 0, 3. X equals 0, y equals 3 at that point. So be careful, because the temptation is to say from negative infinity to 3, right? Because we see a 3 there. But remember, we're talking about the domain. Where is the function 2x plus 3? And that would be from negative infinity to this spot right here, but the x value is 0. So we're going to say from negative infinity to 0, including 0. And the reason why we say it's including 0 is because we have the square brackets represented. The point is filled in, and that's when we use the square brackets. Okay, now from 0, not including 0, so this point here picks up again, but it's an open circle, so it does not include 0, and then we go off to infinity. So we're just looking at the x-axis, and so from this point, again, this point here is 0, 1. Don't look at the 1. Know that we're looking at x values, so we're starting at 0 and going to infinity. So we say it's from 0, not including 0, to infinity, like that. And so what we've done is we've taken the domain and split it into 2 pieces to show where the function is equal to each respective linear function. And if we glue these 2 domains together, the entire domain is all real numbers, because we go from minus infinity, and then we stop here momentarily, but then we pick up again and head to infinity. And so the domain for the entire function is all real numbers. Now, the next question we have is, what are the function values? And if you look at the graph, you can just look here from at -2. We are at, here's -2 for x, and this is the point at -2, and the y value at that point is -1. So f of -2 is equal to -1. F of 0 would be right here, is x equals 0, and the function is not defined here, it's defined here. So f of 0, plugging in 0 gives us 3. So f of 0 equals 3. And then finally, when we calculate f of 1, we're right here for x equal 1, and it happens to be on the x-axis. The line intersects the x-axis right there. So that's the x-intercept, and the y value then is 0. Now, you don't have to do it from the graph. If you don't have the graph in and you just want to evaluate these, you look at the point that you're inputting and you pick the right interval. So -2 lies in this interval. And so we plug -2 in here. 2 times -2 is -4, plus 3 is -1. 0 is not in this interval, but it's here, right? So we, again, 2 times 0 plus 3 is 0 plus 3, or 3. But here, 1 is not in this interval, it's in this interval. So -1 plus 1 is 0. So you look at the point that you're picking to evaluate, and you find the right interval that it lies in, and then you use the appropriate equation. That's how you do functions defined piecewise. And finally, the question is this function continuous? No, you can see it's not. When a function is continuous, you can draw it without lifting your pencil. And here I'm drawing it, but I have to, at this point, I have to lift my pencil and draw the rest. And so it's not continuous.